been working on for the last few years. And in a nutshell, the problem is the following. We're given a quantum system that is modeled by some Hamiltonian H that will be specified in some way, and we'll talk about this. And the goal is now to use a quantum computer to obtain time-evolved properties of the quantum system. So one way of solving this problem, if not the only way, but one way of doing it, is if we can actually prepare the evolved quantum state in some encoded function, right? So for that, we will need a quantum computer, but this is not necessary, certainly. In this talk, I will focus on that, on preparing the evolved quantum state. And my goal will be to basically to provide a quantum algorithm built upon 1 and 2 qubit gates that could prepare such a state, okay, with some sort of convergence guarantee, saying that the state that I prepare after I apply some quantum algorithm is a state, the evolved state up to some epsilon error. All right, so my talk is mostly about this last point, and I want to give you a warning here, which is the following. So any quantum algorithm that is specified to a problem like this one, I mean, is naturally is going to involve some technical description. So my talk will have some technical content, and I'd be happy, if at the end, I don't expect you to follow everything that I say, but it'll be good if at the end you have an idea, a rough idea, at least of what are the best quantum simulation algorithms that are out there. Have a rough idea of what are the algorithmic tools, the algorithmic primitives. There aren't that many algorithms. I mean, you heard this in various talks. There aren't that many quantum algorithms. And specifically for the Hamiltonian simulation problem, we had to design some algorithmic primitives that were used later in other scenarios as well. So at least you'll have a rough idea of what those tools are. And I also would be happy if at the end you have an idea of what is the status of the problem, what is the status of this in the field, and what are some open problems that you may be interested in working on later. All right. So you heard in other talks about quantum simulators, special purpose quantum computers. My talk is not about this. My talk is not about designing a quantum system that is specific to simulate another quantum system, like an optical lattice, some ion trap experiments and so on. So my talk is basically about using a digital quantum computer for simulating quantum systems. So the problem of quantum simulation was the main motivation behind Feynman's proposal of a quantum computer. Feynman noticed that simulating, for example, an n-spin quantum system with a conventional computer required time that was exponential in this n, little n, which is the number of qubits, say. So in principle, quantum computers are not subject to this exponential explosion. And this is what Feynman noted, and that's basically where one of the motivations of quantum computer was born. So we now know that quantum simulation has numerous applications, not only in physics, like, for example, computing scattering amplitudes, in QED, I mean, simulating quantum field theories, computing correlation functions, perhaps even computing equilibrium properties of quantum system, applications in quantum chemistry, quantum transport, and so on. But we also know now that quantum simulation appears as a subroutine in many other algorithms. One main example is the algorithm for solving linear systems, or a quantum version of the linear systems problem. That algorithm uses Hamiltonian simulation as subroutine. So whatever progress we make in Hamiltonian simulation, quantum simulation, I mean, that progress will be carried to other algorithms as well, to other problems. Moreover, we now know that many problems related to computing properties of quantum systems are problems that are BQP hard or even BQP complete. There is a nice paper in 2006 by Pavel Boysen and Zhang, where they show basically that if you find ways of dealing with a quantum simulation problem on a quantum computer, pretty much any other problem that can be solved with a quantum computer reduces to it. So in this sense, Hamiltonian quantum simulation is the problem for a quantum computer. I recently wrote an article about this, and in my view, I think quantum simulation will be the application of quantum computers, at least the first applications for it, because we believe that there is an exponential speedup, and this problem, I mean, it's of a broad importance that is something that will be naturally implemented in such a computer. So, although there are some, hundreds or even more papers of Hamiltonian simulation problems, I want to point out that we still need more advances on this in order to take quantum simulation closer to reality, okay? So we know that quantum simulation can be implemented efficiently on a quantum computer under some general assumptions that make sense, physically reasonable assumptions. But I want to clarify that we are not here after approaches of complexity, say, n to the lemma, right? I mean, we really want to nail out the problem and get the complexity as small as possible. So a natural question is whether quantum simulation is the application for near-term quantum computers. In my opinion, this may be, okay? Certainly, I mean, it makes sense to try to analyze something related to simulating quantum systems with such devices. Such devices have limits on the number of qubits, limit on number of gates, but we still may enter in some region where something useful can be done in terms of quantum simulation. So we still don't yet know. One of the big issues of these NISQ devices is that many of the quantum algorithms that people are trying to implement, they use no quantum error correction. This can be an issue if you are looking for accurate results at the end, okay? So I would say that the question of whether simulating physical systems with NISQ devices, I mean, that still remains fairly open. Any advance could be very useful. There is a lot of interest on this recently, but in my opinion, I think we need more results and even better problems. I think that many of the problems that people are looking at are kind of like the bar is too high, and we probably will have to lower the bar in order to do something interesting, still interesting, okay? So, but I would say that beyond these motivations, it is often the case that even Hamiltonian simulation methods that are aimed for fault-tolerant architectures, they also provide the basis for even other near-term methods. One example is the product formula that we'll talk about today. All right, so quantum simulation is an extremely active field of research. If you check the archive, there's pretty much one or more papers every day on this topic, okay? And while a lot of progress is being made, and a lot of progress is being made actually fairly recently, I think there are many important questions that remain open. I'll talk about those. And as I said, I mean, one of the main things is that if anything related to simulating quantum systems will be done in the near future, we still need of improved Hamiltonian simulation methods, okay? So my goal in this talk will be to summarize some of the most useful techniques for this problem and results, okay? But certainly there won't be enough time to go over every existing result because, as I said, I mean, there's hundreds of papers on this. Also, I will pick some simple examples to lower kind of like the technical content, okay? But I will clarify at the end that the results that I present can be generalized to simulating more complex quantum systems and even address other more complicated models for this problem. All right, so I assume that you can still hear me well, right?
Yes, we can.
Okay. I mean, it's strange to talk when there is silence.
Yeah, I know. No, everything is fine.
Okay, cool. So, I mean, the simplest example would be to take an n-qubit or n-spin one-half system, right? Because if my quantum computer is made out of qubits, then, I mean, the coding process is not that complicated. So I start with a little n-qubit system, okay? And I will say that that qubit system is modeled, the interactions are modeled by some Hamiltonian that takes that form. It's a linear combination of some operators, all right? For simplicity, I'm going to assume that these operators are products of poly operators, okay? And these coefficients are real numbers. I mean, certainly the coefficients may have units of energy or things like that, but all the things are, we can take care of that. But for now, I mean, these real numbers may not have units, and the Hamiltonian is just a simple linear combination of poly operators, poly products. Poly products are nice because they are unitary operations and they are Hermitian at the same time. So, I mean, I can use those properties for when I describe the Hamiltonian simulation algorithm. for example, I mean, a Pauli product could be like flipping the state of the qubit J and qubit J plus 1. That is an example, right? So I assume, yeah, I've seen the previous talks, and some people already talk about Pauli operators and so on. So I don't have to probably go through this.
Rolando?
Yes.
Are you assuming locality here? So any further assumptions about those Pauli products?
I am making no assumptions yet, okay? But certainly, and once you start putting constraints on what type of operators you have there, I mean, locality assumptions and so on, then you can use that structure to further improve your simulation method. So for now, it's fairly general. It's just a linear combination of Pauli products, all right?
Okay.
There is this big K, capital K, right? Which is, the number of terms. And I put this constraint on the coefficients that are bounded between 1 and -1. I mean, that doesn't have to be the case, but I mean, this is kind of like with no loss of generality, because if those coefficients do not satisfy that condition, then I can renormalize them and absorb the constant in the evolution time, right?
Right. Okay.
So in matrix representation, I mean, these matrices are huge. I mean, they are of dimension exponential, 2 to the n by 2 to the n. But I'll never write such a matrix, right? I want to avoid anything that scales exponentially in this little n. So someone writes on a paper what the Hamiltonian is, okay? And we have plenty of examples where this is the case. In condensed matter, we typically write Hamiltonians in this way. Okay, so what is the Hamiltonian simulation problem? I mean, so far I've been talking distinctly about quantum simulation and Hamiltonian simulation, but now I'm going to get into a little bit more detail. So the Hamiltonian simulation problem is basically approximating the time evolution operator, okay? So we're giving some Hamiltonian H, for example, as a linear combination of Pauli products, an evolution time that may be positive, okay? Some precision parameter epsilon, which is greater than 0, and the goal, I mean, the basic goal would be to construct a quantum circuit, a quantum algorithm, which is a concatenation of these operations V from V0 to VL minus 1, such that when I implement that V in some state psi, I prepare some pure state which is close to the evolved state, all right? How close? Well, how close it depends on that epsilon, which is an input to this problem. And this has to be valid in general for all pure quantum states psi. All right, so we can generalize this definition a little bit, okay? So in this version, we now allow the quantum circuit not only to act in the initial state psi, but perhaps we introduce new ancillas, which may be initialized in some state 0, okay? So now this V, this quantum circuit, quantum algorithm, acts on a larger Hilbert space, but at the end, what I prepare is something where I can decouple the ancillas from the state that I want it to. So if I observe the qubits related to the state that I prepared, then I'm going to be epsilon close to what I wanted to prepare, all right? And you can go even, I mean, more general, right? You can think even of a quantum channel, and Graham talked about quantum channels so far, where I take my quantum channel, I input the state, okay, which is psi, and now I want that quantum channel output something which is close to the evolved state that I wanted to prepare, okay? Epsilon close. And here I'm using the trace norm because the trace norm is a suitable norm for this problem. I won't be able to distinguish the state prepared by the quantum channel with the actual quantum state with an experiment with probability greater than epsilon. All right. So the main objective here is not only to develop a quantum algorithm that prepares the state within some epsilon error, okay? But we want that quantum algorithm to be efficient, and we want that quantum algorithm to be as efficient as possible, all right? And by efficient, I mean complexity that, at most polynomial in the interesting parameters like the system size n, the evolution time t, and the inverse of the precision 1 over epsilon. All right, so a quick review of quantum algorithms. So in quantum algorithm, I mean, this is the way that it looks. Basically, we prepare some simple initial pure state, okay? Maybe the state psi with some ancillas which are initialized in 0. Now, next, we implement the unitary evolution as a sequence of these V gates. And at the end, we are going to make a measurement of an observable and to obtain, some useful information about the state that we prepare. So for the Hamiltonian simulation problem, our goal is basically to take our quantum system, somehow encode that quantum system in a quantum algorithm. And then at the end, if we were interested in computing some correlation function, time-dependent correlation function, then we are going to make some measurement, and that from that classical information, we'll decode the information that we wanted to, all right? Like the correlation function. So when constructing a quantum algorithms, what we are interested in are what are the resources. So those resources, I mean, come in many ways. For example, the total number of qubits, the number of fresh auxiliary qubits that we need, okay? The number of measurements, the number of repetitions, perhaps, of the algorithm that we have to do in order to obtain some accurate results. Certainly, the number of 1 and 2 qubit elementary gates, okay? And perhaps we have even to take into account what is the additional classical complexity from encoding, decoding, from pre-processing, post-processing. On variational algorithms, this classical complexity may be a big factor, okay? So all the things contribute to the overall number of resources of the quantum algorithm. Depending on the technology, the architecture that you're using, some of the resources may be more expensive than others, right? In some cases, you may be interested in reducing the circuit size. In some other cases, you may be interested in using less antennas and so on. So we look into all these things when we design quantum algorithms. All the things are important. So in the Hamiltonian simulation problem, we basically are trying to find an approximation to this exponential operator, right? The evolution operator, e to the minus iht. So we want to find such an approximation by a sequence of, say, of elementary 1 and 2 qubit gates. And as I said, not only we are seeking efficient algorithms, but we are looking for the best possible method in terms of overall resources. And those resources, I mean, depending on the method, they will be, some of the resources are optimized in one of the methods, some of the other resources are optimized on another method, and so on. And those will be, I hope, will be clear when I describe the different methods. So from here, you can clearly see that, any quantum algorithm that tries to approximate the exponential operator, certainly, I mean, we have to get into technical details. It's like asking what is the best algorithm for doing matrix multiplication. You certainly need to understand at some level some technical details in order to prove up on the previous algorithms that were available. So the story here is the same. We are trying to approximate the exponential operator, this e to the minus iht, as a sequence of 1 and 2 qubit gates, as I will explain later. All right, okay, so I say we're looking for the best possible method, right? But there's certainly limits on how good the method can be. Elizabeth talked a little bit about this yesterday. So there is what we call the no fast forwarding theorem. I think Patrick also mentioned something. So the no fast forwarding theorem puts limits on how good your Hamiltonian simulation method can be, all right? So there's many versions of this non-fast forwarding theorem. A couple of versions are what we call the so-called query model. I mentioned a little bit about this at the end of my talk, but basically what it says, roughly what it says, is that if you're given some Hamiltonian h, okay, that under some reasonable assumptions on the Hamiltonian, and now you want to evolve your Hamiltonian for time t, okay, or this time tau that is here in the theorem. You need at least order tau queries, okay? So roughly what this is telling you is that no matter what your Hamiltonian simulation algorithm looks like, if you are trying to simulate a Hamiltonian for time t, you need something that is at least linear in t number of gates, 1 and 2 qubit gates, okay? There's generalizations of this that also include precision, right? So the previous theorem doesn't tell you anything about precision, kind of is assuming constant precision, but if precision now is something that you care about, then a version of this theorem is telling you that, if you're the number of gates or queries, okay, to be more precise, also has to be lower bounded by some function that depends on this precision. And that function is this strange function, which is the logarithm of 1 over epsilon over the log of 1 over epsilon, okay? But it's telling you that if you can't achieve zero, error with the finite size quantum algorithm for Hamiltonian simulation for all instances at least. All right. There's versions of this in the gate model that really focuses on what is the number of gates rather than number of queries, but the things may be related. Again, I mean, the spirit of the theorems is that you cannot do better than having a quantum circuit that is in size is at least linear in the evolution time. It has to go linear. Okay. All right. So here are some of what I think are the key frameworks for quantum simulation. For many years, people always thought about doing quantum simulation using the so-called product formulas. Okay, so there was the seminal paper by Seth Lloyd in 1996. And then things started to change more recently. In 2012, there was a paper by Dominic Berry and Andrew Childs on how to use quantum walks for the Hamiltonian simulation problem. They achieved some nice scaling in terms of evolution time, but the scaling was not that nice in terms of precision. More recently, in 2015, we came up with this idea of using a Taylor series approach. Okay, and we improved upon everything that was previously known about this problem. So that kind of like steered a little bit the field, and people started to investigate even more techniques for Hamiltonian simulation. And I would say another key framework was developed later using similar ideas to this Taylor series approach. It's called quantum signal processing by Low and Chuang, and there was a paper in 2017 about this. And in my talk, I will kind of mostly focus on the rest of my talk on product formulas and the Taylor series approach. I mean, these are two things that I work a lot on. And I will also mention how these quantum signal processing ideas work, okay? So you have an idea of what are the most important results and how these methods work in general. All right. Okay, so now I'm going to jump into how these methods are constructed. So are there any questions at this point?
I don't see any.
All right.
So we can go on. If I see something, I'll let you.
Okay, so I wanted to introduce so far, basically what the problem was, and what are the techniques that are available, at least the most important techniques that are available. And now I'm going to go into more detail into each of the techniques. So I start with product formulas, which are fairly easy to understand, okay? So these product formulas, they are kind of attractive because they are simple, they are intuitive, they are even already used in classical algorithms such as Monte Carlo, path integral Monte Carlo. I mean, they are based on these product formulas. For implementations on a quantum computer, they do not require ancillary qubits, okay? Which, this feature may make them attractive for near-term applications. If additional qubits are expensive, then let's try to have a simulation method that uses the least number of qubits possible. So the basic idea is that these product formulas, they approximate the evolution operator by short-time evolutions under the terms in the Hamiltonian, the constituents, okay? And each of these short-time evolutions can be simply simulated using just a few 1 and 2 qubit gates. All right, so it's fairly simple, the idea. So one nice feature of these product formulas is that they exploit some structure of the problem, some structure of the Hamiltonian, such as the commutation relations. And when such a structure can be exploited, they perform actually fairly well. Not only they're simple, but their complexity, is fairly good. But if the structure cannot be exploited or is unknown, the performance at the end may be poor compared to other methods. Another downside is that the complexity, as we will see in terms of the accuracy, this epsilon is kind of also poor. And this could become kind of like a killer if you are interested in doing quantum simulation with high precision. And certainly, certain areas in physics require such high precisions, like simulating, in QED or QCD. All right, so how does this work? So again, we start from our Hamiltonian, which was a linear combination of poly products, okay? So the evolution operator is this exponential, e to the minus iht. Now we're going to approximate the exponential, as I said, as a concatenation, basically, of short time evolutions under each of the terms, okay? Order in some way. There's no specific order in here. So it's clear that, if your evolution time were to be 0, right, this evolution operator is just a trivial operation. And in that case, if I choose all my s's, which are the short times here, to be 0, then the approximation is exact. All right. The other nice thing is that each of these short time evolutions, under the assumption that these operators are just poly products, they can be easily decomposed into one or two qubit gates. Okay. So the complexity of the quantum algorithm at the end is mainly determined by what is the number of terms in the product. All right, because our quantum algorithm will be constructed based on this product that is here, replacing each of these exponentials by a sequence of 1 and 2 qubit gates. All right. You may wonder, like, okay, so does this really make sense that the complexity, the overall complexity, is the number of terms in the product? Because if each of the s's is very small, then it appears that I'm evolving with Hamiltonians for a very short time, and short time evolution should be less expensive than longer time evolutions. But for this case, it is because each of the poly products are basically, our s's are kind of like multiplies. So no matter what these s's are, then I will have to represent each of the terms in the product by some short quantum circle. Okay.
Rolando, you have a question from Carton.
Yes.
Where did the CK term go in the expansion?
Yeah, that's a good question. That will go in the way that we basically define our s's that I didn't talk about. Okay.
Okay, thanks.
All right. So one example here on how to decompose, say, if your product was of 3 terms, okay. I was talking about 1 and 2 qubit gates because that's a set of universal gates. This is way of decomposing to 1 and 2 qubit here into 2 sequences of 2 qubit gates. I mean, these compiling techniques are very well known in the field. All right. So I'm going to take a simple example. Okay, say that my Hamiltonian is just a sum of 2 terms. All right. Here, the constants that Carlton was asking about, they are just 1. And I'm going to define the following unitary. It's just evolving with one of the terms, okay, followed by an evolution with the other term. So if I do a Taylor series decomposition of this, then I notice that, first order, I recover the identity operator. Sorry, 0 order is the trivial operation. The first order is just the sum of the 2 Hamiltonian terms, and then I have something of order S squared. If I look at my evolution operator, right, in this case, well, the first 2 terms are of the same, they look the same, right? So the difference between this W1 of S and the actual evolution operator is order S squared. In this case, we say that W1 of S is a first order approximation to the evolution operator because the error is order S squared. So in this case, the idea, if we want to approximate, say, our evolution operator for evolution time t, okay, then what we're going to do is the following. We're going to approximate the u of t as a sequence of, or as a product, okay, of these first order approximations for sufficiently small times s. All right. So r here is what we call the total number. It's basically what is, the number of segments in this approximation. And if we can I hide this, are you okay? Well, anyway, so for some reason I'm something is blocking my slides. Probably it's not blocking yours. So if we search for say precision error epsilon, then a simple calculation is telling you that the number of this total number has to go quadratic with the evolution time over the precision over epsilon. All right. Right. Okay. So in that case, basically, I'm going to end up approximating my evolution operator by just R products of W1 of S, okay? And each W1 of S is just a short-term evolution with one Hamiltonian and the other Hamilton, okay? Fairly simple. And it's a good approximation because it satisfies the error bound that we wanted to. You know, as physicists, we can always make the problem more complicated, right? And we can seek, for example, what we call high-order Trotta-Suzuki approximations. So these are product formulas that go beyond first order, all right? So when we have many terms, the first order approximation that I talked about before is just a product, you know, of evolutions with each of the terms. So here are the CKs that Carlton was asking about. So if we do that, one can show that this approximation is a first order approximation. We can go beyond, okay? And now there is a way of constructing a second, this is a third order approximation, okay? In which it's kind of like we first evolve with the terms, okay, for time, you know, like 1/2, say, in one way, and then we go the other way, okay? So here, you know, we start with, say, the 0 term, and we go all to the k-1 term, and here we start from the k-1 term, and we go all the way to the 0 term, and one can show that this is a third order approximation, all right? So we kind of increase the number of terms from the first order to the second order by just a factor of 2, but we increase the order of the approximation by a lot. There is a recursion that can be shown, and this is, you know, this W2P of S that calls the previous, basically, order approximations to increase the order over and over, all right? So this is well known. You know, I mean, the evolution times have to be chosen in a particular way, okay? And it can be shown that if you take, say, you know, the pth order approximation to the evolution operator defined in this way, then what that means is that the error between the short-term evolution under Hamiltonian and a short-term evolution under this product pth order approximation scales, you know, with the evolution time to the pth plus 1 power times some lambda, which has to depend on the norm of the Hamiltonian, right? I mean, the energy scale has to enter somewhere. So this lambda here is defined as just the sum of the absolute values of the coefficients that define the Hamiltonian. Is this okay? I assume if there's no questions.
Yeah, it's all good. Thanks.
Okay, so I hope it's clear. I mean, the rough idea here, I mean, what I'm seeing is that one can develop high-order product formulas in a recursive way, all right? And they satisfy this error bound that we have here.
Right.
So if we want an epsilon approximation, right, we're going to play the same game as before. The evolution operator for time t, now the large time t, will be a sequence, okay, of these product formulas for short time s, okay, r times. We have to pick this r such that the error is epsilon. So a way, right, I mean, following this bound here, one can easily see that, you know, I mean, the overall error will be r times the thing that we have here, right? So that will imply that r has to scale in this way with the evolution time and the precision. All right. So this p is basically the order of the approximation. And at the end, the number of gates, right, which will be the number of products in my formula, because we're defining it recursively, each time, each higher order is calling 5 times the previous one, right? There is a square, 1 square, so it's 5 times the previous one. Roughly, the gate number, the gate complexity is going to go with 5 to the p from the recursion, okay? Times k, because each of the product formulas involves, right, I mean, the k elements in the Hamiltonian, times the number of segments, this Trotter number here, all right? So at the end, yeah.
So, Rolando, so the optimal p is not known a priori, right?
All right, so that is a very good question, because if I look here, right, I mean, if I look at the Trotter number, it looks like as p grows, then the Trotter number decreases, right? So that gives you, you know, a hint that maybe it's better for you to go to very large p's. P is something that you can choose. It's the order of approximation that you're going to implement. But when you go to the gate complexity, you see that there is a factor that also is growing exponentially with P. All right. So there is kind of like a trade-off. When you look at the overall gate complexity depends on this way. So it's not clear anymore that large P is the best thing to choose, because you have this factor that is growing exponentially in P. So this can be optimized, all right? And people play these games. And in fact, they play them actually for particular instances of the problem, for particular simulation, for simulating particular Hamiltonians, like Hamiltonians in quantum chemistry and so on. Because in that case, perhaps the constant is not really 5 to the P, but maybe something smaller, okay? And then when you optimize, you get a different P, all right? So P infinity is not the best, P1 is not the best, all right? It's something in between. Is that a good answer? Did you like it?
Thanks. Yeah,
okay.
yeah.
Okay, I made you believe that it was the right answer.
It looks like it.
Yes.
Thanks.
In practice, though, because in practice, when you look at say methods, for example, Monte Carlo methods and so on, people just use first and second order approximations, and again, I mean, they look at different complexities for the particular instances, and probably if they're happy with the second order approximation, that's where they stop. All right.
You have another question
yes.
from John. Why is W2 the third order approximation rather than the second? Is the second order defined by a different recursion method?
Sorry, the second order approximation and is this one here. Is that the question? Sorry. Well, can you tell me the question again? What is?
Why is W2 the third order approximation rather than the second?
Sorry. I said the third order. That was wrong. It's a second order approximation. W2 is a second order approximation. All right. So the W sub P is a p-th order approximation. This is like a 2p-th approximation. This is second order approximation, and so on.
All right, good.
All right. I'm sorry if I said third order approximation. Yes, it's a second order approximation. Meaning that when I take this difference with W2, then the thing goes with basically with s to the cube power. Okay. All right. Okay. So again, I mean, nice thing about this is that there are no ancillary qubits. Okay. So I say, the method is efficient, and this is related to your question, but how well does it perform in practice? Polynomial scaling may not be enough. Okay, especially if you're dealing with a P which is not, if it is 1 or 2 and so on. So, yes. Okay, so actually, there's been in many papers looking at this, how basically what is the complexity of product formulas in practice. Okay, and I'll talk a little bit about this just to tell you, what is out there. So people have looked at this quantum chemistry problem. Okay, so this is maybe a fermionic Hamiltonian. It can also be written as a linear combination of polyproducts, right? So I'm going to make just a few assumptions here for simplicity. I mean, you don't have to make those, but say that the evolution time was a constant. The coefficients are bounded by constant, the precision constant, and so on. Okay, then it turns out that if you were to plug in everything, just naively into what we had before, the error bounds, then and you look at the second order approximation, then it turns out that the number of gates was ridiculously large. All right, even though for many years we thought that the Lois paper 1996, that basically this is what it did, it was good enough because it was an efficient method. When you still really start to plug in numbers for particular instances, I mean, these polynomials can be huge. Certainly, k to the 11th is something that cannot be managed. All right, and people have looked at even if we wanted to make something better than a supercomputer, even with a quantum computer, even if the method was efficient, we had to take the age of the universe. I mean, to simulate something reasonable. All right, so this sparked a lot of interest on how to reduce this complexity. There's been papers on circuit compilations, how to cancel some gates. So I give you the circuit and how do I need all the gates, or can I compile it in some way to reduce its complexity? This has been done in some papers in 2013. They reduce the power by 1. Then they notice, that the error bounds from the error bounds for product formulas for this particular problem were actually better than what I said. Okay, and what I give you were upper bounds. So you can improve those upper bounds and reduce the power by 1. Then they saw that when they did some numerical simulations, they really needed, power to the 8. Okay. Again, there's been a number of papers from many of them coming from the Microsoft group. Then they even further improved the error bounds. They reduced the error, the scaling to the 6th power. Even taking other decompositions of the Hamiltonians, show even better scaling. And and here maybe I'm kind of like repeating what Elizabeth said yesterday, that if there is an efficient algorithm for some problem, right, that takes polynomial time, but the power is huge, then history shows that that power can be reduced by a lot. And this is one example of that. We started with the power, k to 11. We went down to k to the 6. Even numerical simulations, that's better. Then, sorry. Okay, so, and then people even look at further improvements of these product formulas approximations, okay? And there's been a couple of recent papers, very recent, last year and this year, on how randomization actually can help, all right? So these are the two references here, 5 and 6. So, is there a question? Sorry.
No, there are.
Okay.
Oh no, actually, no. I'm sorry. There is. Were these numerical simulations performed for specific Hamiltonians?
Yeah, for the quantum chemistry problem. Mm-hmm. Yes, for some particular molecules.
Okay, thanks.
Yeah, I cannot tell you exactly, what they simulated, but yes, they work for specific instances of the problem. All right. Yes.
I'm sorry. There's another one. Is the gate count taking account of the fact that you can implement any single and qubit gates? In other words, will the gate complexity scale badly if we further try to decompose those gates using the gate alphabet available on quantum computer?
Yeah, that is an excellent question. So, yes, I was assuming that you could do any 1 and 2 qubit gate, but there will be an overhead if now you take a discrete set of universal gates. But the overhead, we know that it's not that bad, and people have been looking into this problem, during 2014, 15, and so on. There is what we call the Solvay-Kitaev, theorem that basically tells you, that you can approximate any 2 qubit gate by a sequence of discrete gates fairly efficiently, and this has been done. Yes.
Okay, thanks.
So
I don't see any other question. You can go.
Okay, cool. All right, so I'll talk a little bit about randomization. I skipped through this actually fairly quickly. I just want to give you an idea that, we can do something more on product formulas. And sometimes very simple ideas actually, improve the methods significantly. All right? So let me take, for simplicity, just the first order approximation. So the first order approximation involves with each of the terms on the Hamiltonian, okay, in some ordering. All right? Start with O0, O1, and so on. I apply each of these only once. So I say that this is a first order approximation, so the error is order S squared. And I told you that the complexity was going with the evolution time square over the precision. All right, it's something that I said already. Okay, so this paper of Earl Campbell basically what it does is the following: you're going to pick a term, okay, of the Hamiltonian with some probability pk that is proportional to the weight of that term in the sum. Okay, this lambda is the L1 norm, is the sum of all these coefficients ck. All right. And then I'm going to apply a unitary, which is just evolving with that single term, right? So I'm not evolving with all the terms as I did with the first order approximation that I showed you before. I'm just picking one randomly, and I'm evolving with that guy. If you do that, really, I mean, you're taking your state, right? Your initial state probably was a pure state, and now you converted this into a mixed state because I'm picking things with some probability, all right? So this is rho prime, it's a quantum channel, okay? With probability pk, I apply vk to my state. If I do a Taylor series expansion of this, of the new quantum state, rho prime, then I can see that at first order I haven't done anything. Sorry, zero order, I haven't done anything. At first order, basically, I do this operation, right? I mean, this is just, you add with exponentials on the left and the right, and then I have something at order square. But if I can rewrite this thing as saying I apply the actual evolution operator for a short time s, okay, to my state, and the approximation error was a square. So this is, again, is a first order approximation, all right? But that uses only one term of the Hamiltonian, all right? So it's a very simple idea and it works. So what this does is it reduces the gate complexity, okay, of the first order approximation W1 of S that I talked to you about in the previous slide by a factor of k, because I'm just applying one term rather than all the terms, all right? And the final gate complexity, it goes, again, with the evolution time square over epsilon, but there is no factor of k, all right? So this can be a big reduction if your Hamiltonian has many terms. In fact, I mean, you may deal with Hamiltonians that have an infinitely large number of terms, and as long as this L1 norm lambda is bounded, then this method works, all right? Because there is no k complexity here. It depends on this lambda, all right? Which is the sum of the coefficients. So this was interesting. There was another improvement via randomization by Charles et al., where, if you remember, the second order approximation had this structure, right? I first started with the term 0, and it went all the way to term k minus 1, and then I started from term k minus 1 to term 0. But nobody told you which was the term 0 and which one was the term 1, and so on, right? I mean, there is some arbitrarity in how you can choose the order of the terms in your Hamiltonian. So the idea of this paper is basically tells you pick them randomly, okay? And if you pick them randomly, it's interesting, but you improve the error bounds, all right? So here is a simple example of why this works. Take again the first order approximation, all right? And, I mean, so here I was talking about the second order approximation, but I'm gonna describe, one of the reasons why this works by using the first order approximation, because it's simpler to analyze. So first the first order approximation, all right? So you can write it in this way. This is something that I told you already. And when you look at the error between the first order approximation and the actual evolution operator, I told you that I was going with S squared, all right? In reality, if you do a more careful analysis, it goes with S squared times the commutator between the two operators, all right? This is it's a simple result that you can do it. You can do the exercise. Now, if you, if you pick now O0 first and O1 next, then the commutator flips. It flips sign, because now I have to, sorry, this should be O1 and O0, not O1 and O2. Then it flips sign. So if you take the sum of the two things, you kill the second order term here. So the idea in this case could be, well, pick, first O1 and then O0, say with probability 1/2, or pick first O0 and then O1 with probability 1/2. That's, again, it's going to give you a mixed state, but it's going to be very close to something that is pure. And when you look at what is, the approximation error that I made here from the actual evolved state that I wanted to have is order S cubed. All right? So you can do similar analysis for larger order approximations. So, here I went from a first order approximation to a second order one, right? In general, for larger orders, you don't increase the order by one, but you still can show that you can increase, you can get better complexity bounds if you use this trick of picking the order of the terms randomly in the expression for the second order approximation. All right. Okay, so we can further, we can even look at more things, like, the previous complexity depending on quantities such as the L1 norm of H, right? So what happens if, for example, say, well, this L1 norm makes sense if I'm exploring the whole Hilbert space, but if I'm constrained to working in some low energy subspace, maybe, I don't care about the whole norm of the Hamiltonian, but I only care about, some small norm of the Hamiltonian that is constrained to that low energy subspace. So there's been a recent work by Burak, who's a postdoc at lanl, and myself, that basically, looks into this problem, and we can show that the error bounds for product formulas can actually be improved when you constrain your initial state to be in a low energy sector. Okay, we don't have to care about the whole norm of the Hamiltonian, right? Because we never explore the whole Hilbert space. All right, so here's a few more references about product formulas, and this, I think, it concludes my description of how these product formulas work. So, are there any questions at this point? It's kind of like a natural stopping point.
Kunal is asking another.
Okay.
How are we picking terms randomly for higher order approximations using C sub k of a lambda?
That's a good question. Maybe I wasn't clear. So you pick the order randomly only once, okay, for the second order approximation. And then the higher order approximations are just defined recursively as I showed. So once you define the second order approximation, then the other ones come from that one. But you're right. You may be interested in randomizing things for higher order in a different way. And this hasn't been looked at as far as I know.
Okay, thanks.
Sure. All right, so let's move to the Taylor series approach, okay? And this, is in our paper, if you want more details, in 2015, and I will explain you how that works. Is there another question?
Yeah. When randomly choosing gates in the approximation, do you have to take an average of the results of many compilations? How does the number of compilations require scale as n increases?
That's a very good another very good question. So in the previous approaches, okay, so in the approach where, by Chelsea et al., then the complexity per each realization basically has the same complexity, right? In general, this is not the case when you take a randomization approach. And yes, you may be interested in things like what is the average complexity. Okay, certainly that's useful, right? But sometimes we are after, whenever we have a randomization approach, then we not only care about the average complexity, but we also want to say something like, going twice past the average, or, that probability decays exponentially. Okay. Yeah, so if the tails of this probability distribution decay exponentially decay fast, then that's a good thing, because the average complexity kind of tells you, you'll never go more than a constant times the average. All right.
Okay. Yeah. Wait. There's another one.
Okay.
If you have two terms in your Hamiltonian with a very large commutator, does trotterization not work well? Are there better ways to handle this case?
Yeah, so if the commutator is bad, the error is going to be bad. So in that case, maybe, trotterization is not the best approach. Okay, and I'll talk about other approaches now. Okay. So yeah, the error bounds, when the commutators are not good, you are kind of like, basically attaining the bound, right? The upper bound. So that may not be good. And this is known, and some of the improvements that I explained before basically deal exactly with this issue, grouping terms in the Hamiltonian such that the commutations between those terms are kind of small.
Okay, thanks.
All right, so I jump to the Taylor series approach, and I hope I have, yeah, okay. So again, so the idea here is a different one. Instead of approximating the evolution operator, okay, as a product of evolutions on each of the terms, I will attempt to approximate the Taylor series expansion of the evolution operator. All right. So I have the Hamiltonian as I had before, and now, the approximation error is going to come up from the fact that we have to put a cutoff into the Taylor series approximation. All right, I cannot go to the infinite order, so I will have to put a cutoff, and this is going to give an error, in the approximation. So if the order R is large, then this operation here is almost a unitary operation, right? Because it's going to be a very good approximation to U of S, which is unitary. And one thing that we can note here is that when I look at W of S, once I replace my Hamiltonian by the linear combination of polyproducts, which are unitary, this is a massive linear combination of unitary operations once I replace H. So the algorithm that I will describe basically will attempt to implement such a linear combination of unitaries. All right. So that would be, basically the algorithmic primitive that we'll use here. All right. So as before, for some technical issues, I will have to split the evolution time into segments, okay, into Q segments here. And so S is going to be small, roughly small, but not too small. And then I'm going to try to approximate the evolution operator for time S, small time S, with this linear combination of unitaries primitive Q times, basically. All right. So another quantum primitive that we had to design for this problem is what we call OAA, that stands for oblivious amplitude amplification. So LCU will be for linear combination of unitaries, OAA for oblivious amplitude amplification. And I should point here that these two primitives actually been used for many other problems beyond Hamiltonian simulation. All right. Okay, so we know that quantum computers can implement unitary operations, but what about linear combinations of unitaries, right? So this is what I've been talking about. So now I'm going to explain you how to do this. So suppose that I have a pure state psi, and now I want to map psi to some, operator acting on psi, okay, which is a linear combination of, alpha and beta are here positive numbers, for example, with no loss of generality, and V1 and V2 are unitary operations, okay? So I want to make that transformation, basically, all right? So there is a simple gadget to do this, actually, which is the following. On some qubits, we input the state psi. We add one ancillary qubit that is initialized in the state 0. We apply a rotation to it such that the state prepared of that single ancillary qubit encodes the coefficients in the linear combination, the square roots. It turns out that the square roots are the optimal way of doing this. Then I implement one of the unitaries conditional, say, on the state being 1 of the ancilla, then V2 conditional on the state being 0, and I apply the inverse of this original operation. So if you follow what this quantum circuit does all the way to the end, then at the end you can see that there are kind of like two branches flagged by the ancilla. One contains the state that we want, and the other one something that we don't want, okay? So at this point, if I were to measure the ancilla and I obtain 0, then I'm done. I prepared what I wanted. I made the transformation that I wanted, right? But because there are these two branches, in principle, these two branches have amplitude which is greater than 0, and different from 0. Then if I make such a measurement, I will have a probability of failing, okay? The probability of failing is going to be given by the norm of this state square, if you work it out. All right. It turns out that if I put a further constraint in which the linear combination of unitaries, okay, matches exactly half of another unitary, all right, and this alpha plus beta is equal to 1, there is another trick which we call oblivious amplitude amplification, such that, if I call this whole operation W, and I apply W, I make an operation on the ancilla, which is a reflection, the inverse of that W, and so on, you can work it out that at the end, with probability 1, okay, you implemented the linear combination that you wanted to implement. All right? So this trick is called oblivious amplitude amplification. I can, I'm going to explain you now how it works, okay? But basically, you need this extra assumption that the unitary, okay, is the linear combination of unitaries is exactly half of the unitary. All right, so how does this work, right? So I told you, if I implemented the W, okay, only one, I have the branch of the state that I want and another branch of the state that I don't want. So if I measure 0, I'm good. If I measure 1, it didn't work, all right? But if the linear combination was exactly half a unitary, I can think of this linear combination, okay, as being, I can represent these states in the following way, in a two-dimensional Hilbert space. This is the overall state, W0 psi, okay, I represent with this vector. And now I'm representing this part, okay, as another vector. And because this is exactly half of a unitary, I know that the overlap between this guy and this guy is exactly 1/2, all right? This implies if I make this representation, the angle between these two things is exactly pi/3. All right, so the idea of this Olive's amplitude amplification is to take the state that I prepare, make a reflection over this axis. If I do that, I map this state into this one, okay? And then I make a reflection over the original state again. And if I do that, I map this state into this one, which up to a minus sign is what I wanted to have, all right? So that's where, this extra assumption of the linear combination being half a unitary is important, because I know that the angle is exactly pi/3. If I didn't know this, then I wouldn't know what the angle is. And this concatenation of reflections, okay, that makes all these rotations in this two-dimensional Hilbert space is not guaranteed to give me a state that is exactly what I wanted to have, all right? So these are the ideas used in Grover's search algorithm, for example. It's called amplitude amplification. Here we go one step further because we don't really know what the state psi is. I never told you what it was, right? It could be whatever. So we don't have to make any assumption on that state, and this idea of amplitude amplification still works. So at the end, when this linear combination is half of a unitary and I implement this gadget, I basically end up having what I wanted, all right? In a more general case, half of a unitary may be a larger linear combination of unitaries, not just two. In that case, we can do a similar circuit, basically. It's just that now we need more ancillary qubits to encode all the coefficients in the linear combination of unitaries, all right? But the trick, is the same, basically. We later implement this conditional operation in ancillas, and we implement the inverse of that unitary. You can show that there's a branch of the state that we want, another branch that we don't want, but we call that W. We use Olive's amplitude amplification that calls that W 3 times, okay? And at the end, I prepare exactly the linear combination, okay, applied to the state whenever we satisfy this condition. All right. So what happens here? I told you that I'm going to approximate the evolution operator, at least for a short time, as a linear combination of unitaries, right? Once I replace my Hamiltonian by the linear combination of polyproducts. So I write down all that huge linear combination now, but I know that it has some form. It's just a linear combination of unitaries. It can be represented in the way that I want. So in order for these coefficients, okay, to satisfy, okay, so these coefficients here will depend on the evolution time, right? It depends on the evolution time. So in order to satisfy that condition that the whole linear combination now can be made, right? Half of a unitary, I need to pick my evolution time in a special way, all right? So once I pick the evolution time in that special way, then I'll be able to say that that linear combination, all right, is almost half a unitary, okay? This W of S, right, is what it approximates the evolution operator. So this now is not exactly half a unitary, but it's almost half a unitary. So that's the reason why I have to pick my S in some way. All right. So once I'm at this point, I'm basically fitting the framework of linear combination of unitaries and Olive's amplitude amplification approaches. So the goal now is basically to apply the gadget that I showed you before. Okay. So I know that for that particular value of S that we had to pick, okay, to match this half of a unitary approximation, then the number of steps will go with T over S. Okay, it's going to be given by that S. So that implies that the number of steps is going to be linear in T times lambda, because my S had to be picked as the inverse of the L1 norm, right? This is what I showed in the previous slide. Furthermore, I need to pick the error, okay, the order in the approximation such that per segment, right, this is an approximation of error epsilon over Q. I have Q segments, I use the union bound, so then the overall approximation error is going to be epsilon. So this is going to tell me that the order, okay, where I have to stop where I have to put a cutoff in the Taylor series has to depend logarithmically in 1 over epsilon, okay, in the following way. So this is actually the key thing of why this method depends, the complexity of the method is only logarithmic in terms of precision rather than polynomials in the product formula. It's because this approximation in the Taylor series, I can put the cutoff, okay, in an order R that only depends logarithmically on the inverse of the R. All right. So at the end, when we look at the gate complexity of this method, it's going to be basically Q times, what was the gate complexity of this LCO plus Oblivious sample amplification approaches. All right. So when you put everything together, one can show that the overall complexity for this method is almost linear in the evolution time up to this logarithmic overhead. Okay, almost linear in the L1 norm. But it has a very nice dependence in terms of precision that you could not achieve with the product formulas. Okay, so this is what basically is the appealing part of this method, is that the precision in terms of, the complexity in terms of precision is only polylogarithmic. All right, so this showed that it was a strict improvement over any previously known approach for Hamiltonian simulation at the time. Okay, and we could also show that the gate complexity in G in terms of precision was optimal, because remember when I told you about the non-fast forwarding theorem, I gave you, a function of log over log log in terms of 1 over epsilon. We are achieving that, at least when the evolution time is a constant. All right. As I said before, these approaches were later used for many other quantum algorithms. All right, so people look at implementations for quantum chemistry. They've been able to reduce powers even more, not only improve in terms of precision, but even in terms of complexity, as a function of the number of terms in the Hamiltonian. All right, so this is kind of like another natural stopping point, because I want to devote my probably the next 10 minutes to go quickly through the last approach that I mentioned, which is quantum signal processing. Are there any questions at this time?
I don't see other questions at this point. Oh wait, there is one.
Okay.
How does the error in simulating U over 2 appear in the final scaling?
How does the error of?
The error in simulating U over 2, so this half unitary, appear in the final scaling?
Oh, you mean the error that is coming from approximating the Taylor's series by putting a cutoff? Because I'm dealing with the W of S, which is not exactly U of S or something like that. So here, the overall error is epsilon. So, we pick everything such that the overall error at the end is epsilon, basically. And so the algorithm, right, is a concatenation of Q steps. Each step is trying to approximate the evolution, okay, for time T over Q with precision epsilon over Q. This is what sets, the cutoff, basically. All right. And then at the end, there's going to be a complexity associated to each of the steps that is going to depend on this R. All right. It's linear on this R. I have to multiply that Q times. Okay. And I told you I have to just make Q to be almost linear in evolution time in subspecies.
Okay, thanks.
Okay. But the overall idea here is, right, using these two primitives, linear combination of unitaries and oblivious amplification, use them together, so we can implement now linear combinations of unitaries with probability almost 1, right? Whenever, the linear combination of unitaries is itself all proportional to a unitary in some way. All right. Okay, so I'll go quickly through this newer idea that I would say was motivated by the Taylor series approach, and it's what the authors call quantum signal processing. Okay, so the main result here, without going into too many details, is the following: is that when they look at the complexity, right? Sorry, I forgot something. Okay, So when we look at the complexity and the number of ancillaries that we needed in our method, so in the Taylor series approach, then what one realizes is that the number of ancillaries depends on the evolution time. It's a mild dependence. It's just logarithmically, okay? The precision error, okay? But increases, increases with evolution time. And the complexity was also, the product between something that was going linear with time with some function that was logarithmic in 1/epsilon, okay? So what they can show here using this method is that complexity actually, instead of being the product of these two things, is the addition of these two things. So it's a mild improvement, right? But still is an improvement. And typically, even if the improvement is mild, the ideas that the authors propose are nice ones, and certainly are nice to look at them because they can even be applied in other contexts. The other nice thing is that the method of these ideas of quantum signal processing, they require a number of ancillaries that do not depend on the evolution time. Okay, so they may depend on the number of terms of the Hamiltonian, the dimension, and so on, but it does not depend on the evolution time. And this is one of the things that we needed, for our algorithm on Taylor series. All right. So how is that this works? Okay. So yeah. So this is what I said. So the basic idea is roughly similar to the Taylor series approach. We're going to try to implement, the evolution operator on some state psi by applying an operator, okay, maybe acting on a larger Hilbert space now. But this operator is now a linear combination, or if you want, a polynomial on some unitary W of R. All right. So here you already see that this problem is again related to the problem of function approximation. The better these functions approximate the evolution operator, the better I will do. All right. So in particular, and these ideas have been used even before this work, I mean, there is a so-called Jacobi-Unger expansion, okay, that approximates the exponential of some real x that is bounded by 1 by some linear combination of, where the coefficients are, scale, they depend on the Bessel functions of the first kind, okay, times exponential of this form. This is called the Jacobi-Unger expansion. And it's fairly easy to show that you can, this sum runs over infinite numbers of R, right? But you can carry it off at a value of R that is almost linear in tau, okay, plus logarithmic in 1/epsilon. And this is kind of like the key thing of why they achieve such a nice scale, because they can carry off the series at that point. We had to carry it off, differently, in a different way in our Taylor series approach. But here, this is a better approximation in some way. All right, so again, I don't hope you to follow all the details here, but let's assume for the moment, that there is some additional property that my Hamiltonian up to, this L1 norm can be, this is what is called a block encoding of the Hamiltonian, but can be seen as a unitary operator, but as a block of a unitary operator, okay? Suppose that you have, we make this extra assumption, okay? Then, for example, in our case, I mean, we could assume that our unitary was this thing here, conditional on some ancillary state being in K. I implement the poly product of K, right? And then my state G could be this linear combination. You can plug in the things here, and you can show that when you do that, you obtain exactly, this sum over CK of OK, CK OK, as we had, before. So then one can build a unitary, all right, that depends on this U and other reflections in some way. And what happens at the end is that if X were to be an eigenvalue of H over lambda, then the eigenvalues of W are this e to plus minus r cosine of this X. So what I'm trying to do here is to develop a W that somehow, can use this result of the Jacobi-Unger approximation, all right? One can also show, more properties of this W operation, and not only the eigenvalues of that W depends on the eigenvalues of the Hamiltonian, but also the eigenstates are related to the eigenstates of the Hamiltonian. So at the end, what happens is that, if this W is the one that I defined in the previous slide, I can approximate the evolution operator by this linear combination, this polynomial in that W. So at this point, you may use the idea of implementing linear combination of unitaries that I explained you before, all right? But again, I mean, you have to use this oblivious amplitude amplification and so on, so there is an extra overhead into the complexity. So what they've done, this quantum signal processing approach, was basically define now a new primitive that implements a polynomial as a function of W. And that primitive is fairly simple. It just uses one ancilla. It makes a rotation on the ancilla, it applies a conditional operation W, makes another rotation, conditional operation W inverse, and so on. So when you look at the end, what happens here, right? Basically, what you've done is implement a polynomial in W. So the main question now is, like, given the coefficients in a particular polynomial W, can we find this one, qubit rotations? So what they show in the paper is that this is not always possible, but for a special problem of Hamiltonian simulation, you can indeed find such phases. All right. So this adds, an additional step, like a pre-processing step, where you have to compute the phases. All right. And there's been a couple of works along these lines on what is the complexity of doing that. And I believe that Anders Somberger and Ingrid Subasi also look at this problem for both and Lano. So I'm not an expert on, on how to obtain the phases from the polynomials, but there's other people that you can ask if you are interested. All right, so I'm almost done. All right, and then yeah. So maybe are there any questions about quantum signal processing at this point?
I don't see any questions.
Okay, I assume that people are getting tired already. All right, so I'm about to finish. All right, so now I'm going to tell you about things that I haven't talked about. So I mentioned that there are other methods. There are methods based on quantum walks. Okay, there's a paper by Berry and Childs in 2012. Those methods are nice. They have nice scale in terms of evolution time, but perhaps not in precision. But in general, I mean, the take-home message here is that there's plenty of methods, okay, powerful methods, and at the end, it depends on what is the problem you're looking at. One method may be more efficient than others, all right? So, I mentioned that I was considering Hamiltonian, which was just a linear combination of poly products, okay? I didn't talk to you about the query model. The query model basically assumes, like, you can query the matrix elements of the Hamiltonian, all right, in some particular way. And there's these methods that I talked about can also be applied to the query model. So, again, in the query model, you may not only be interested in what is the gate complexity, what is the 1 and 2 qubit gates, but also what is what we call the query complexity, how many queries you need to use, right? Because queries may be expensive and you may be wanting to minimize the number of queries at the expense of increasing other 2 qubit gates, for example. So these things, people have looked at the things. So, I assume that the Hamiltonians were for qubit system, was time independent. Certainly product formulas, Taylor series approaches can be also generalized to the time dependent case. Okay. It turns out that the Taylor series approach have a very mild complexity overhead when the Hamiltonian changes in time, which is nice. All right. But it turns out that, for example, the quantum signal processing approach is unknown on how to actually use it for simulating the evolution operator with time-dependent Hamiltonians. So, I assume that it was for qubit system, but you may wonder what happens with my system is made out of fermions, anyons, bosons, and so on. There's also been works along these lines. Many times the way to do it is by reducing the problem that uses a different statistics, particle statistics, to one where the statistics is that of a qubit system. Right? So simulating bosons may be more complicated because perhaps you have to deal with Hilbert spaces which are of infinite dimensions, so you have to put extra cutoffs in Hilbert space dimension and so on. All right. There's also works about simulating quantum systems with continuous variables or simulating quantum field theories. So I'm working on this problem. There's a paper in 2015 by himself, and there's been a paper about simulating quantum field theories by Preskill, Lee, and Jordan as well, that they look at this. Again, the main challenge here is that degrees of freedom that may be infinite, right? So you have to deal now with a quantum computer that is made out of a finite number of qubits, so you have to put cutoffs and so on. All right, so some of the problems, one which I think is interesting is whether the complexity of product formulas can be further improved, especially in terms of precision, because they don't scale that nice in terms of their epsilon. Can we generalize ideas of quantum signal processing to simulate time-dependent Hamiltonians? Okay. Can we reduce the complexity of other Hamiltonian simulation methods under further constraints on the initial states, like, for example, low energies, symmetries, and so on? Okay. And as I said, the different methods are powerful in different instances. We always wonder whether there is one, like the method, okay, that can address, all instances and give the best of all the worlds, basically. All right, so I'm done. So thank you very much.
Okay. Thanks, Rolando, for an excellent talk. Are there other questions? Okay, from Carton, would it be feasible to make specialized hardware for the sole purpose of Hamiltonian simulation?
So, okay, so what I think is probably, it is my belief that it's going to go the other way. Experimentalists will design the hardware that they can, all right? And we theorists, we have to design, at least, in the near term, our problems such that they match the hardware. So I don't know in the future, but in the near term, this is what I see. Maybe the answer to your question is yes, but I don't see that happening in the near future. In the near future, it's going to go the other way. So people will design, the hardware that they can with the architecture that they can, and then it will be up to us to fit our simulation methods into that hardware.
Okay, thank you. There's another one. Alan Aspuruguzi recently explored variational methods for simulating transmon qubits using a quantum computer. Will this area of research lead to a blow-up in quantum processing power, as quantum computers are used to design better quantum computers, analogous to the AI singularity?
Oh, I have to read this question. Let me see. Okay.
Do you see the chat window?
Yeah. Now I can see. Okay, so I don't know the answer to that. I'm certainly not an expert on variational approaches, and I don't know about the scaling of this particular variational methods for simulating transmons qubit. So I don't think I can answer that question, to be honest. I fear that at least from what I've seen, many times these variational approaches are nice, right? Because they provide new ideas and are intuitive and so on. But sometimes the lack of convergence guarantees. So it is unclear to me, how things in reality scale when you don't have such a convergence guarantee. In fact, even verifying whether a state, right? If you see a variational algorithm as some sort of state preparation algorithm, that that now you have to verify whether you prepare the right state or not by computing, some cost function and so on. I would say that even that state verification procedure can be expensive. So I don't think I can answer that question. I would be happy to see more, variational approaches that come up with some sort of convergence guarantee in which we can assure that the state that's been prepared can be prepared with certain time and so on. So, yeah, I don't know. I can't answer that question.
Okay, thanks. Here's another one. Do we have optimal scaling results for any of these algorithms? That is, lower and upper bounds matching for the gate query complexity.
Yeah. So these are the results that I mentioned about the non-fast forwarding theorem. I don't know if you've seen that slide, but I would say there's at least 4 results on this that are known. And a couple of them are in the query model. So in the query, we know that at least we need order T queries, okay? In terms of T, we know that we need at least log 1 over epsilon over log 1 over epsilon, okay? That's queer function, okay? In terms of precision, again, in the query model. We prove that in our paper. And if you are interested in, in terms of case beyond the query model, then, there's this result by Aharonov saying that if you can simulate a quantum system with less than order T gates, then BQP is equal to P space. That is not going to happen. And there's some other result by Hastings, I believe, and Kochari along similar lines, but they use time-dependent Hamiltonian. So yes, there are those lower bounds, and the Taylor series, both the Taylor series approach and the quantum signal processing approach, I mean, they match those lower bounds. Perhaps, there may be some constants that can be optimized, but at least asymptotically, they do match it. So, by construction, we have the upper bounds as well.
Okay. Okay, Kunal is happy with your answer.
Okay.
All right. Are there any other questions?
Can I ask one more?
Yeah, go ahead.
Yeah, go ahead.
So in the beginning of your talk, you kind of said that maybe these methods would be relevant for NIST, maybe not. It could go either way.
Yeah.
I presume you're familiar with these 2 papers by D-Wave, the high-profile ones on like 3D Ising spin simulation, and then also XY model. Do you have thoughts on those? Is that not a witness that this is possible in the NIST era?
Yeah, so I'm aware of that paper, but I haven't read those in detail. So I mean, what is the? Yeah, maybe.
As I understand them, they're both basically just doing simulation of those systems, the Hamiltonians, and showing phase transitions that occur in different regimes.
Yeah.
So, and a big effort that they're putting into those papers is that the metrics that they're measuring can't be replicated with classical alternatives. To me, this seems like a great witness that this is possible.
I see. Yes. I said that again. I mean, honestly, I don't know. I know about the existence of those papers. I don't know the details. So this is what I think, right? So I do believe that with NISC devices, or maybe at some point, not too far in the future, or even, the quantum supremacy experiment may be an example. Okay, there can be things, we could do things that cannot be classically done at this time, right? But more focused along the lines of physics simulation. Now, if you ask me whether computing ground state energies is one such application, I don't believe that is, because that's setting up the bar too high, right? We do have imprecise classical methods that work very well, okay, and they give you imprecise results. So if you don't care about precision, then it's going to be hard to beat classical algorithms for physics simulation. So we have kind of we need to find some sort of a problem in which perhaps precision is not such a big issue, okay? But still we can answer some question with a NISC device that we cannot answer with a classical computer. And I've started to see some works along those lines, especially, for example, for frustrated models, right? Where classical methods fail miserably, right? So maybe, you can decide, you can lower the bar by asking questions like, like in the local Hamiltonian problem. Is my ground state energy, above or below something, right? So you are not looking for a very high, precise quantity, but it's just kind of like a decision problem. That would be useful. If you can, if you can claim that there exist states for certain systems whose energy is below what it was known before from classical methods, then that's certainly a win. Anyway, I don't think I I have much more to say about this, but if I see, some applications of these devices in the near future to physics simulation, I think we have to be smart on picking the problem, all right, in lowering that bar, and we have to be smart to make sure that such a problem fits well within the architecture that is available, right? So I think these are the two main things that we should probably focus on, or at least people are interested in this problem should focus on.
Great. Thank you very much.
Sure.
Okay, I don't see any other questions.
Okay, I mean,
So,
yeah, you guys can also, email me. I mean, I'm available, right? So if you have further questions and you don't want to ask them now, then you can send me an email.
Okay.
Yeah.
Let's thank Rolando again for an excellent talk.
Well, thank you very much.
Yeah. So, all right, everyone says thank you. Okay. Thanks a lot again.
Okay, thank you very much for setting this up, Lucas.
Thanks. Bye bye.
Yeah, thanks.